wonderful month of Astronomy on Tap. We have two fabulous talks coming up for you in a little bit. But we are going to start the night off with some Nobel trivia. Maybe, if my clicker works. You want to tap me forward, please? Maybe? Well, that works. Haha! Great. So we're going to start with trivia. I just want to point out a small mistake. We're going to skip forward to the first question. And you're going to notice that it is labeled number 1. We're going to go through from 1 to 10, but on your lovely trivia sheets, they go from 0 to 9. So either renumber them if your heart so chooses, but just remember 0 is 1, 2 is 3, you know. We're making it up as we go. So thank you very much, and enjoy trivia.
Whoever gets it. If you were smart about the picture. Yeah. Why aren't those pieces of red tape evenly spaced?
All right, I'm going to move on to number 3. There we go. How many people were awarded the Physics Nobel Prize in 2017 for the observation of gravitational waves? A is 3,240, B is 1,011, C is 12, and D is 3. All right, so now I'll move on to number 4. Eventually. Wait for it. There we go. To how many people can the Nobel Prize be awarded for a single discovery? A, 10,000, B, 100, C, 3, or D, 1? Alright, so number 5. True or false? Vera Rubin was awarded a Nobel Prize for her observations of galaxy rotation curves, which led to the discovery of dark matter.
I see the tires.
True or false question? All right. All right. Number 6. When Donna Strickland, won the Nobel Prize in Physics in 2018, she became the blank woman to do so since the inception of the award in 1901. Is that A, first, B, 12th, C, 3rd, or D, 20th? All right, moving on to number 7. Oh, there we go. True or false? Einstein worked alone to develop the theory of general relativity. Is that true or false that Einstein worked alone to develop the theory of general relativity?
Catherine, you're wanting to get together at some point this weekend to do play date or board games.
All right, moving on to number 8. True or false? The Higgs boson is named after Peter Higgs, who independently postulated its existence in 1964. So again, another true or false question here. All right, on to number 9.
If you will not get bitten, you may get cheese or general.
That's fine with me.
Okay.
Alright.
There's another true or false question. Marie Curie was originally intended to be excluded from the 1903 Nobel Prize for the discovery of radiation. That's again another true or false question. Marie Curie was originally intended to be excluded from the 1903 Nobel Prize for the discovery of radiation. And lastly, we'll do number 10. And number 10 is, true or false, the Nobel Prize is a just and egalitarian method of recognizing the contributions that great individuals make to science. True or false?
Huh? Yep. Oh, yeah. Good girl.
We just go back and scroll through them again, right? I might not reread them.
Nope.
Just
Just X out of it.
Before I introduce our first speaker of the evening, I would just like to ask everyone to bring up their trivia sheets to our trivia czar in training. He's killing it. He's doing a great job already. Just like a real czar. Wait. Thank you very much.
I ripped them up, put them in my pocket.
All right, it looks like almost everyone has brought up their trivia sheets. Thank you very much. If you're still debating your answers, you can bring those up until, well, do it soon because we're going to start grading. All right, our first speaker of the night is a second-year graduate student at the University of Washington in the astronomy department. She studies the intersection of astronomy and data science. Please welcome Leah Fulmer.
All right, hello everyone. My name is Leah Fulmer, and tonight we're going to be talking about astronomy's most intriguing discoveries, the ones that happen by accident. So the first thing that I want to do is I actually want to acknowledge that we are currently situated on the traditional lands of the Puget Sound Salish and Nuwamish tribes. Furthermore, I want to thank the cleaning and maintenance staff of this building, as well as all research facilities mentioned in this talk, without whose labor this work could not be conducted. The only way that astronomers learn anything is by observing. So the universe is filled with light, and it is our job to gather that light and create some sort of physical narrative that explains why everything looks the way that it does. But there are so many ways to observe the universe. So if I'm an astronomer trying to judiciously think about how I should observe the universe, I need to think about what types of objects I want to observe. Do I want to look at a planet, or a star, or a galaxy? Because what I'm going to learn about the universe is going to be really different depending on what types of objects I look at. I need to think about what wavelength we're looking at. Galaxies look really, really different in the ultraviolet versus the infrared. So we have to make a decision about how we want to look, what types of light we want to look at by their wavelength. I got to think about cadence. So this is how often do I want to observe the things that I want to observe. Some astronomical objects, my favorite ones, they change in brightness over time. So if I'm looking at an object every 30 seconds, I'm going to get a lot more information than I would if I looked at that object once a year, for example. I have to look at what part of the sky I want to look at. So we exist in a galaxy, which means that sometimes when we look out, we are looking at the galaxy that is our galactic home. We're looking at all the dust and stars in our galaxy, but other times, if we're looking through the pole of the galaxy, we're not seeing any of that. So different parts of the sky offer different information. We can think about duration, so how long we would like to look at an object. Do we want to look at it for 15 seconds, or do we want to look at it for, say, 100 hours? That's going to come back. So if we look at something for 100 hours, it's going to tell us a lot more information about what we're looking at than if we only look at it for 15 seconds. And finally, we need to think about brightness. So we can say, I definitely want to look at galaxies, I definitely want to look at them in the ultraviolet, but depending on that object's distance, some ultraviolet bright galaxies are going to be very bright when we look at them kind of like in the night sky. But then others, if they're very far away, for example, they're going to be very dim. And so the brightness, the inherent brightness of objects, mixed with how far away they are, mixed with the sensitivity of our telescopes, again, can give us really different information. And we have to make a decision about what we're going to look at. The exciting part is, though, that really, every time we look at the universe in a new way, we discover new phenomena that we never even expected to see. So that means that each time we took one of these elements and we looked at the universe in an entirely new way, we found something that we could have never foreseen. And tonight, what I want to do is I want to look at 3 different examples of when that's happened historically, but then I want to introduce the instruments that are coming online in the next decade and think about what new things we might see given new instrumentation. So in 1960, NASA was trying to think about communication by satellite. So we were communicating via radio waves for a very long time, but we want to figure out how to do this over very long distances. So what they did was they built these really large, like metallic spheres that they sent off into space. And the idea was that on the West Coast, someone would release a radio broadcast. It would bounce off the sphere, and then someone on the East Coast would try to observe it with a radio telescope. Simple, right? Well, it turns out that between 1960, when these were launched, and 1964, when our telescope to observe them was built, they didn't actually need this technology anymore. And so NASA was left with this instrument that really had no particular purpose. So 2 astronomers, Penzias and Wilson, decided to try their hand at radio astronomy, which was this new emerging field of astronomy. We're going to look at the stars in radio waves for the first time, which is, I think, kind of exciting because, like, we had been communicating to each other through radio waves for like decades, and so Penzias and Wilson were like, what is the universe trying to communicate to us? You know what I mean? Very exciting. So radio observation is difficult, though, because radio waves are everywhere, right? That's kind of the point. You can stick out your radio antenna and it'll just catch a bunch of them. But when you're trying to look at something very specific, like the sky, you want to make sure that you are actually getting your signal from where you want it from and not from everything else that could be at play, right? So Penzias and Wilson did a very careful job of making sure that there was no interference, that all other signals were muted or very quiet, so that whatever we found from the universe would be very clear. And what they found was far louder than they ever expected. They discovered this like huge, super loud radio signal coming from everywhere in the universe. And at first they didn't believe it. They were like, this can't be right. We've never heard of anything like this. This is absurd. It's probably our detector. It's probably New York, something like that. So they painstakingly quieted the signals from all these things. They took out some pigeons that were trying to nest in the horn. And yet, they still found this pervasive radio signal. So a modern understanding of this signal looks like this, or a modern observation of it looks like this. This is a map of the sky. If it were taken out from all around you and slapped on a 2D, this is what you would see. And the color variation represents 2.7 Kelvin plus or minus 200 microkelvin. So a very, very tiny variation all across the sky of this consistent about 3 Kelvin signal. And they didn't know what it is, but they were like, okay, we're going to call it the cosmic microwave background. Cosmic because it comes from the cosmos. microwave because the strongest signal peaks in microwave wavelengths. They were using a radio telescope, but microwave is just right next to it. So the peak signals in microwaves, and background because it is so pervasive throughout all of the sky. Meanwhile, some collaborators at Princeton were trying to think about the origins of the universe. They had this idea that there might have been a Big Bang that would have started the universe, but they knew that they needed to find evidence for this, right? So they were thinking, well, if there really was this Big Bang, it would have released a tremendous amount of radiation right at the start. And as the universe expanded, all of that energy would dissipate over the volume of the universe. As the universe got bigger and bigger, that energy dissipating over larger volumes, it would get cooler. And if that really did happen, these are a lot of ifs at the moment, if that really did happen, we would probably see some sort of signal all over the sky at about the same temperature. And that is exactly what Penzias and Wilson found. So by accident, they took this telescope that NASA had built for satellite communication, they stuck it out there, and they found literally the origins of the universe. This changed our understanding of astronomy and physics as we know it, and it was a really, really big deal just by looking at something in a new wavelength. Oh, that's the cosmic microwave background. Exactly, and so, ooh, wow. Oh, side note, this is kind of fun. So, again, Penzias and Wilson didn't actually think that they had found what they found, or they didn't think it was real, right? They didn't think it was a real signal. And it turns out that like a lot of people had actually found this signal previously, not thinking it was real. In particular, Andrew McKellar found the CMB, the cosmic microwave background, in 1941, but asserted that this signal will have its own, perhaps limited significance. He basically said, it's probably nothing. And we later learned that it was literally the origins of the universe. So, you know, never underestimate yourself. Okay, so that is one way in which we look into the new universe, or this universe, and in a new way, and we discover new phenomenon. Another way that we're doing this is through duration. So in 1990, the Hubble Space Telescope was launched. It came back with these super blurry pictures. Everyone was really upset because that's really genuinely very sad to send out your telescope and have it come back blurry. But they did what they needed to do. They put some glasses on the telescope, and they were coming back with these really remarkable images. Okay, and so the director of the Space Telescope Science Institute, which launches Hubble, he said, I have this really, really good idea. How about we look at nothing? And people were like, what are you talking about? He said, why don't we look at the darkest part of the sky that we've ever seen and just put Hubble there for 100 hours and see what happens? So people were really upset about this for a couple of reasons. Hubble's a very valuable telescope. It matters what you do with it for the time that you do it. 100 hours is a very long time to look at what we think might be nothing, okay? Second of all, we actually at this time did not have a really good idea of how many galaxies were in our universe. People thought it was like, I think like 10 billion. So they were saying, just statistically, no matter, like if we look at this very tiny part of the sky, we're probably not gonna see all that much because there's probably not that many galaxies in our universe, right? 10 billion over a universe is a low density. Almost like a vacuum of density. Okay, anyway, so the director said, you know what, I can do what I want, because that's actually, the thing about these things is if you're the director of this telescope, you get this thing called director's discretionary time. You really can do whatever you want. So said, I'm gonna do whatever I want you to look at it, let's go. And they did so, and what they found was remarkable. They found what's now known as the Hubble Deep Field. They found an incredible plethora of galaxies that they never expected to see. So there's so much going on in this picture, so I want to break it down just a little bit. Some of the objects in this image are foreground stars. So they're stars that are in our Milky Way that just happen to be in our field of view, but we know that they're foreground stars because they have these fun little crosses which describe, or like, they're a result of the relationship between the light and then interference with the telescope itself. So We know that those are in our Milky Way. But what we also see is nearby galaxies. So we know that they're nearby because they're really big, just like the way our eyes work. If something is very close to us, it takes up a lot of space in our field of view. So these galaxies are really big, but we can also see some of their internal structures, which is very, very exciting. Equally exciting is that we can see really far away galaxies. So every single little dot in this image is an entire galaxy of light, because at that distance you only see very bright things like galaxies. But that means that every single dot in here is the farthest galaxy that we had ever seen in the history of astronomy at this time. So the Hubble Deep Field revolutionized our understanding of how many galaxies were in our universe, and like the shapes of those galaxies and the evolution histories of those galaxies, all because someone said, let's look for a very, very long time at something that we don't know what's going to happen. Let's take the risk, and they did, and it super worked out. Because, yeah, this is amazing. Okay, yeah, and just, yeah. Everything in this image is a galaxy. That is super far away. Okay, all right, moving on. Another way to think about, or one more example, when we look at new types of objects, we get new types, we find new things that we didn't expect to see. So in 2009, the Kepler Space Telescope came out trying to look for exoplanets. So it was like, exoplanets are planets that are outside of our solar system around other stars. And the late aughts and now, exoplanets are very, very exciting. Exoplanets, research into exoplanets is the fastest way to find aliens, so that's super applicable. And we really just want to understand what is it like on a world that's not our world, right? And so the way that we find these planets is actually, so planets are really, really small and they're really difficult to see directly. Sometimes we can do that, but one of the ways that we see planets that are further away is through their light curve. So a light curve just describes the change in brightness of an object over time. And when we look at a planet's host star and its change in brightness over time, if the planet is right in the line of sight between us and that star, we'll see that the planet blocks some of the light from that star. So very bright up here, less bright down here. And if it does so periodically in this very specific way, we know that we found a planet. Okay, so this is called the planet transit method of finding exoplanets. And what actually happens is we observe this star every 30 seconds or so, and we create a light curve so it's kind of bouncing around, but you can see that at some point it dips a little bit. And we can say, okay, we think that there's a planet there, especially if it happens multiple times. If it has a very short period, we can say, all right, we've definitely found a planet, okay? So at the same time that this is happening though, wait, my arms are getting tired. Okay, so at the same time that this is happening, Kepler is collecting more data than we had ever really worked with at that time, right? And so some people were developing computers to identify where these little dips were happening in the data, but we also wanted to ask citizen scientists or non-professional scientists to look at these light curves and help us to identify where the planets were. Right, so they would get a light curve like this. Again, light curve showing brightness over time. These are in days, so over the course of 7 days, how is this brightness changing? And they would say, looky there, we have got ourselves a planet. We know this because the brightness is significantly lower for this period of time and then shoots back up to the stars like ambient brightness, or like basic brightness, right? So we have thousands of people, I think like 300,000 people or something like that, looking at these light curves, and they find this object. So they find this light curve. They say, this is like nothing we've ever seen for a couple different reasons. One, it's very asymmetrical here. So we've got a shallow slope here, but then a steep upslope here. If you'll remember, when a planet passes in front of a star, because the planet is spherically symmetrical, the light curve, the dip in the light curve is also spherically symmetrical. So if this light curve is showing a shallow dip and then a quick dip, maybe something's passing in front of it, but it's definitely not spherical like all of the other planets we know about. So that's suspicious, right? Secondly though, it's lasting many, many, many days. So normally the transit of a planet lasts about a couple hours, but this one was lasting weeks. So that's very different than what we're expecting. So they saw this early on in Kepler's lifetime, and they said, okay, let's look at it for 4 more years. And they did that, and they found even weirder stuff. So when a planet goes in front of a star, normally it creates a brightness, it dims the brightness by about 1%, which is what you might see over here. But then about 2 years into this observation, it dipped 15%. That's more than any other planet could do to a star that we've ever seen, right? And then toward the end of Kepler's lifetime, it was like, I'm freaking wild! And then Kepler shut off, right? So we were like, what the heck? What did you just, so, okay, so, so we have folks after 2013, so modern folks have observed this, star since then, and so we have ongoing research about this star. But to this day, we don't actually know what the star is. We just call it Boyajian star after the principal investigator Tabitha Tabby Boyajian. Sometimes they call it Tabby star. But yeah, so we still don't know what it is. Some options are maybe something like catastrophic happened in front of the star, right? Like maybe something's blocking the light, but it's like it's creating so much dust in the air or something that it's obscuring the star for a very long period of time. Similarly, maybe some like asteroids came and kind of like covered up the star a little bit exactly in front of our field of view. That's not super likely because, again, it would have to happen exactly in our field of view. And then, I mean, there's always aliens, right? Like, maybe there's this civilization that needs energy from its star, so during those moments, it's taking them. So actually, okay, all joking aside, it's probably not aliens. Just because, I mean, it's very precarious for an astronomer to suggest that this might be aliens, mostly because journalists love to say, well, an astronomer said it, so, you know. And it becomes less, it loses its oomph if every couple years someone's saying, probably aliens, you know? So, but never fear, there actually is one astronomer who will always remind us that it might be aliens. There's one astronomer at Harvard who is always down to say maybe it's aliens. We all know who it is. If you're interested, you can Google Harvard astronomer aliens, and you will know. So, this one, if you can't see it, is the title, and then it says, one guess which. So, okay, so it's probably not aliens, but, you know, keeping our hopes alive. And we're very glad that people are still studying Boyajian star to this day. Okay. So again, we're left with these, the 6 items that I've outlined. There's many more. But every single time that we look at one of these realms in a new way, we discover a new phenomenon. What's so exciting about this decade is that one of the telescopes that's coming on in the next decade, LSST, is going to study all of these in a new way simultaneously. So LSST is going to observe half of the sky, the entire half of the sky, every couple of nights for a decade. It has an observational program known as Wide, Fast, Deep. It's going to observe the largest sort of the sky more often and with a very high sensitivity telescope. So astronomers are essentially casting out a net of a telescope, trying to catch whatever they can about the cosmos, right? And the truth is we don't really know what we're going to find. But we know that every time we observe the universe in a new way, we discover new phenomena, right? So my job, LSST comes online in a couple of years. My job, and we know when it does, in whatever, 2022. 2022 actually is very accurate. When it comes online in 2022, we're probably going to be observing things that we've never seen before. So I and others have that amount of time to develop an algorithm that is going to be able to systematically identify the things that we've never seen before, and tell us that we got them. So I'm going to be specializing in anomaly detection. So yeah, anomaly detection. Anomalies are things that we've never seen before. We are going to try to systematically detect them, even though we have no idea what they look like, and could probably never imagine them to this day. So these are simulated observations. These are simulated observations of what LSST will observe. We've got a black hole activity over here, some sort of typical supernova, and then a superluminous, super bright supernova over here. And my job is to take this information and build an algorithm that says, yes, I have seen this go up and down before. Probably not that new, but say, maybe over here nothing has ever been that bright. That's probably super new, right? And so we're going to be trying to think about both anomalous observations. So if an object's light curve looks pretty typical, but then something shoots up or it loses some flux, kind of like Voyage's star, we want to know, right, if there's only a particular number of strange observations. But we also want to know maybe that object is oscillating, that the brightness of that object is oscillating in a way that we've never seen before. So maybe the entire source itself is anomalous. We also want to think about theorized anomalies. So much like the CNV, there are theorists who say, this type of object should probably exist, or that type of object. They would be rare, but they should probably exist. And so we want to be aware of theorized anomalies that people have thought up already, but we also want to be aware of completely unforeseen anomalies that no one has even thought to ask if it exists. We want to be able to find those too. So the kind of moral of this story is that we don't know what surprises we might find, but that's what makes it so exciting, right? That's what makes it so exciting. We get to go into the office every day and say, how do I build the best tool to tell us what we've never seen before? And that's that. Thank you. Oh, questions. If anyone has questions, I would love to answer them. Yes. Oh. Ooh. The question was, am I excited about James Webb? Yes. And yes, I'm very excited about it. Yes, I'm very excited. And I don't know when it's going to be here. So just to save my energy resources, I'm going to be latently excited until it's launched. Then I'm going to be super excited. Any other questions? I thought I saw another hand here. Oh, yes.
For your radio wave explanation, I have a correlation versus causation question. Sure. How do you know that that's what caused this? That's what caused the Big Bang?
That's a ooh, wait. How do you know the Big Bang caused that signal?
Yes.
That is a wonderful question. Okay, love this question. All right, so one second. I want to put this down for maximum hand talking. Okay, so yes, how do we know? That's such a good question. So I mean, okay, so again, the Big Bang released all of this energy. As the universe expanded and the energy dissipated, at temperature, the energy cooled, right? So the energy probably had a specific temperature, and then as the universe expanded, it cooled, right? So we have a theory of how much energy was released because we know how much, we know how much matter is in our universe, and we have an idea of the volume of our universe, or at least our observable universe. And so we have an idea of that amount of energy divided by this amount of volume. What temperature should that be? And it is exactly the temperature that we see. Now, there's always a possibility that that could be a coincidence, but the specificity with those two line up, and the fact that the CMB has so few fluctuations, it's basically the exact same temperature all over, tells us that it is a very, it tells us that it's a very strange phenomenon that is very probably connected to the Big Bang itself. So yeah, the consistency of the CMB temperature and the connection between our theoretical temperature and the observed. Yeah. Thank you for your question. Any more questions? Oh, we got one more, I think.
Is the survey you guys are working on, is that data going to be public at some point?
Yeah, that's a great question. So they asked if LSST data is going to be public. Yes, yes. So eventually LSST will have public data. But for the first 2 years when it's commissioning, when they're making sure that the telescope is doing what it's supposed to do, only particular universities will have that data. So the university is one of the major funders and founders of LSST, and so we will get that data like a year earlier than everybody else, but then yes, it is meant to be a public telescope, which is super exciting. Maybe there will be a citizen science project with it. Of course there will be. Fun.
How much data is that going to be?
Ooh, yeah, great question. So how much data is it going to be? Okay, so it's by the time it's done with its its 10-year survey, should be about 60 petabytes. Every night it's a couple terabytes. So more than we've ever seen ever. It's very exciting. And now we're done, right?
All right, everyone, let's give Leah a big round of applause once again.
student in the astronomy department. Please give a warm welcome to Samantha Gilbert.
Hi everybody, my name's Sam. I actually study exoplanet atmospheres for my research, but tonight I'm not going to be talking about that. I'm going to be talking about something entirely different. So for me, the most exciting part of being a scientist is that I get to use data to tell a story. And this sort of makes scientists the authors of our universe, right? But what's unfortunate about scientists being the authors is that we rarely think to write the story of the scientists themselves. So the story I want to tell you tonight has everything. It has science. It has drama. It has egos. It has really esoteric vector math. But also what's interesting to me about this story is I think it really encapsulates a lot of the things that are really wrong with how some people do science today. The main characters of our story are a special subset of physicists called cosmologists. And cosmologists are interested in learning what our universe was like at its very beginning. Sorry, everybody. Okay. So the key to understanding the origin of the universe is this thing called the cosmic microwave background. And Leah sort of talked about this before. So in this chapter, I'm going to do a real deep dive into what the cosmic microwave background is and why studying it is so important. Surprise. Okay. So the cosmic microwave background, or the CMB, is basically just a sea of photons that fills our entire universe. And you'll often see it depicted as this sort of heat map that Leah showed you before, and we call this heat map a CMB sky map. When we say the CMB, we're really just talking about a special kind of light in our universe. Well, what makes it so special? So the CMB is special because it's actually the first light that ever existed in our universe. So what that means is it's the furthest into our universe's past that we can see. And that's pretty amazing, because that means the same CMB we observe today consists of the very same photons that ever first separated from the hot soup of atoms that existed in our early universe. So the CMB formed 400,000 years after the Big Bang. On the scale of a human lifetime, that's the same, looking at the CMB is the same as looking at a picture of the universe when it was less than a day old. So let's see if this works. The clicker's really not working, I'm sorry guys. But basically, it was me as a baby. And I'm showing you my baby picture because I'm vain, but also because I think that the CMB is basically a baby picture of our universe. Thank you, Nicole. Yay! Me as a baby. So the fact that this really old light still exists today is a really, really big deal for anyone who wants to know what our universe was like at its very beginning. Just like looking at your baby picture gives you a glimpse into your past, looking at the baby picture of our universe, the CMB, gives us a glimpse into our universe's past. And when we compare these pictures, the picture of our universe as a baby to the picture of our universe today, cosmologists can actually fill in the blanks between how our universe began and what we see today. So the CMB actually formed after our universe began. There's stuff that happened before it. And what happened before the CMB is the Big Bang that we all know and love. But what happened after the Big Bang, but before the CMB formed, isn't as clear. We're not as sure. Right now, the working model for what happened after the Big Bang is called inflation. So when inflation happened, we think the universe expanded in size by the order of 10 to the 26. This is like something the size of an apple expanding to the size of our universe in less than a second. So an event like that is really explosive, right? So you would think that we'd be able to see a lot of evidence for such an explosive event like this, but weirdly we don't actually see the mountain of evidence that we would expect to see. But there are pieces of evidence that are theorized to exist. So by definition, if inflation happened and the universe did expand really, really quickly, there would have been an expansion in the fabric of space-time itself. And changes in space-time have very special messengers called gravitational waves. Okay, so thank you for bearing with me. Inflation would have induced such drastic changes in space-time that it would have to leave gravitational waves behind it in its wake. And one way to think about this is to sort of imagine a boat speeding through still water. The calm, still water is space-time. And as the SS inflation speeds through space-time, it leaves a wake of waves rippling behind it. And we call these waves gravitational waves. So to summarize, we want to detect the traces of gravitational waves dating back to inflation when the universe was not even a second old. So how can we do something like that? Point it this way. Point where? So as these inflationary gravitational waves rippled through the sea of CMB photons, they should have basically lined up the CMB photons in a pattern that we should be able to see today. It's theorized that the way in which these primordial gravitational waves realign the CMB photons would be visible to us as a signature pattern that we can identify, sort of like a footprint that a wild animal might leave in its tracks. So the signature footprint that these gravitational waves leave behind is this sort of curly signal that we call B-mode polarization. There's the footprint, and there's B-mode polarization, which is sort of the footprint that gravitational waves leave behind in the CMB. And in this picture here, you're seeing the sort of two flavors of B-mode polarization that exist, left-handed and right-handed. And that's going to come back later. So again, to summarize, inflationary gravitational waves print a special polarization pattern on the CMB, and we call this special pattern B-mode polarization. So that's all well and good, but unfortunately, B-mode polarization is actually a really, really faint signal, and it's really, really, really hard to detect. In fact, you need a telescope more sensitive than any previous CMB telescope in history. So B-mode polarization is an extraordinarily difficult thing to detect, but proving it exists would prove that inflation really happened by detecting the traces of inflationary gravitational waves. And making the discovery that proves inflation would certainly win you the Nobel Prize.
You're doing great.
I want the record to show that my performance is flawless and the clicker's performance is questionable at best. Okay, so thank you for bearing with me through the scientific background and the clicker nonsense. But this is where our story actually begins. And in this chapter, we're going to talk about one experiment that sought to detect B-mode polarization and thereby prove that inflation really happened. And this experiment was called BICEP. Okay, so Brian Keating was a postdoctoral researcher at Caltech in 2002 when he came up with the idea for a refracting telescope to detect B-mode polarization in the CMB. He called his telescope BICEP, which stands for Background Imaging of Cosmic Extragalactic Polarization. Not very catchy. Okay, so after building BICEP in the South Pole, the team did their first observations in 2005. And after the successful observing run, the BICEP team realized that they could probably detect B-mode polarization if they just made their detectors even more sensitive. So naturally, they went to build their sequel, which they called BICEP 2. So when BICEP 2 started observing, the team could not believe what they saw. I know that this plot might look like a random smattering of lines, but what this plot actually looks like is exactly the result that you would expect if B-mode polarization was in the CMB. And it has this exact distinctive curly B-mode pattern that I showed you before, and the blue and red regions are meant to represent the different handedness, the left and right handedness. And when they saw this, it was actually an even stronger signal than they had anticipated. So far so good. Everything was looking great for BICEP 2. In 2014, BICEP 2 released their results to stake their claim on the discovery that would prove inflation. They held a press conference at Harvard where they announced to a room full of reporters and the world that they had solved the mystery of our universe's earliest moments. They also filmed a video with the foremost theorist of inflation, Andre Linde, communicating to him that they had basically shown that his predictions were right. And this is a day that most theorists never even get to see in their lifetimes. So Andre Linde and his wife weep, overjoyed by the news that his theory would become law. And to celebrate their achievement, they pop open some champagne. Dun, dun, dun! It's an oldie but a goodie. So in the months following the fanfare around BICEP 2's big announcement, the plot thickened, literally. So over 250 papers were published in response to the initial BICEP discovery paper. And if you don't publish papers a lot, this is a really big deal. You would be a huge deal in your field if your scientific paper got 250 citations in your lifetime, okay? And one of the papers that was written in response to BICEP 2 is the most important paper of all that we're going to spend a lot of time thinking about tonight. And that paper was published by BICEP 2's main competitor, the Planck experiment. And the Planck paper had the one plot that could actually put BICEP 2's Nobel Prize in its grave. And what their plot basically showed is that you could get the entire BICEP 2 signal from cosmic dust alone. Oh, sorry, you're good. So the fact that BICEP 2 had so confidently announced a result that was so quickly disproven had a rippling effect throughout the community, right? So scientists were really horrified because they thought now the public is going to discredit us, they're not going to trust us. Journalists were also horrified because they felt they played a role in spreading misinformation, but also because they felt like they were seeing a really ugly side of the scientific community. So as all of this unfolded in the public eye, the world got to see a part of the scientific community that usually stays under wraps. And Dennis Overby, a New York Times reporter, kind of put it best. He said the sharp elbows, egos, and all were on full display. So the fact that BICEP 2 made this false result announcement is a really big deal, and it made a huge impression on me when I was a young physicist in 2014. So I have sort of a selfish reason for wanting to tell you this story tonight. I've always really wanted to work out why this happened. Why did BICEP announce a falsehood with so much confidence? Also, what the heck is cosmic dust? So we're going to unpack this further. So lucky for us would-be investigators, Brian Keating, who remember I told you was the inventor of BICEP and one of the main scientists on the BICEP 2 team, actually wrote down his account of the events leading up to 2014 when BICEP 2 made their fateful announcement. And he called his book, Losing the Nobel Prize. Maybe he was a little salty. And I think this book is great because reading it gives you an inside look into how BICEP 2 made a lot of really important decisions. How they made important decisions to design their experiment, how to design their instrument, and then, of course, how to share their results. And it also gives you an inside peek into what a really high-stakes laboratory environment can be like, often at its worst. So, with the insights from Brian Keating's book, which I've read for you, I want to revisit the events of 2014. Let's run it back. Okay, so recall that BICEP 2 was going to go after B-mode polarization with even more vigor than its predecessor, BICEP. And BICEP 2 improved upon the BICEP instrument with way more detectors that were also 10 times more sensitive than their predecessors. This time, they also chose to study the CMB only at its strongest wavelength. And they did this because they wanted to try to get their results as quickly as possible. And this is going to come back later, so I really want you to hold on to this one wavelength business. So the last time I showed you this plot, I said it showed the exact beam mode curl pattern we were looking for, and that when BICEP2 observed the signal, it was much stronger than they had anticipated. What I left out is that they were actually really skeptical of this result, specifically because it was so much stronger than they had anticipated it to be. And they had a really good reason to be skeptical. So among the stars and planets that fill our galaxy, there's also a sea of cosmic dust. And this isn't the dust that's, lurking in the corners of your house. It's really dust that contains metals. And metals have characteristic magnetic fields. And it turns out that magnetic fields can also line up photons into a special pattern. So what this means is that when you're looking for a special polarization pattern in the CMB,
Oh my god, sorry.
what this means when you're looking for this special pattern is you have to be able to distinguish between a polarization pattern caused by cosmic dust, which you don't care about, and a polarization pattern caused by inflationary gravitational waves, which you really, really, really care about. And the BICEP2 team was well aware that cosmic dust could masquerade as their B-mode polarization signal. So I want to emphasize something here. Cosmic dust is really not well understood, and this is a really, really, really hard problem to solve. So to the credit of the BICEP2 team, they used 5 different models to try to predict how cosmic dust might affect the signal they were seeing. And when they used these models, their results pointed all to the same conclusion, that their B-mode signal was real. But the stakes were really high, and they knew that they had to double, triple, quadruple check their results. So this is where the one wavelength thing comes back. So remember that BICEP2 decided that their instrument was only going to look at the CMB at the wavelength where it's strongest. So it turns out that only looking at that wavelength tells you nothing about how much of your signal is coming from cosmic dust. So they simply didn't have the tools to figure out if their result was real or not. So they had to reach out to the competition. And their main competitor was Planck. And Planck is a billion-dollar satellite funded by the European Space Agency. And because Planck has so much more money and so much more resources and so much more time, they actually look at the CMB not only at the one wavelength where it's strongest, but a broad range of wavelengths, including the wavelengths that would tell you how much of your signal is coming from dust. So naturally, BICEP2 reaches out to Planck and they say, hey, would you mind sharing your data? We're trying to figure out if we're looking at dust or not. But Planck actually refuses. And this refusal sets off a bomb in the BICEP2 community. And they find themselves playing armchair psychologist. Why wouldn't Planck share their data? Did they already detect the same B-mode polarization that BICEP2 was looking for, that their Nobel Prize was hinging on? Or, as BICEP2 feared, did Planck just find cosmic dust, ruling out a B-mode polarization detection? So among these possibilities, one stood out as the scariest possibility of all to the BICEP2 team. And that was that Planck was going to try to scoop them, that they already had detected the B-mode polarization and they were going to steal their Nobel Prize. So as a result of their fear that they were going to be scooped, BICEP2 made a fateful decision to protect their Nobel Prize. They popped the champagne. So out of fear that Planck was going to scoop them, they hold this Harvard press conference, they film this feel-good video with the theorists behind inflation. But what I hadn't told you before is that when they did all of this to sort of stake claim over their discovery, they actually hadn't put their paper through peer review. So in case you couldn't tell by the audience reaction, that is a no-no. That is a bad thing to do, and that's because peer review is kind of what makes science credible in the first place. It's one really important check against the dissemination of junk science, right? You really need other scientists to independently assess your results. No peer review. So knowing what we know now, that Bicep 2 basically did all these shenanigans to protect their ownership of their discovery before the community could actually verify it. What they did is basically the scientific equivalent of this, I'm so glad you've all understood that. My millennial office mates thought no one would get this, so thank you.
Okay, here we go.
Okay, so what happened here? Again, what led them to make all of these really unscientific decisions that led them down a path of self-humiliation? So let's review the fateful decisions that Bicep 2 made. So first, remember, they designed their instrument to focus only on one wavelength. And remember that focusing only on this one wavelength is sort of a success-oriented approach. It's a success-oriented approach in the sense that, sure, the CMB is strongest at that wavelength, but you don't know how much of your signal is coming from cosmic dust. And as Planck showed, their entire signal was coming from cosmic dust.
Oh, no.
Second, they chose to bypass peer review, again because they were worried about their discovery being scooped. And finally, they did a premature victory lap, where they held a press conference and they filmed a feel-good video with the foremost theorist behind inflation, Andre Lind. So did they do all these things because they're horrible and malicious people who really want to mislead the public? No, of course not. But I would argue that all of these decisions really have one thing in common. And what all of these decisions have in common is that they're motivated by fear, right? So overly competitive environments are part and parcel of an individualistic conception of science. And an individualistic conception of science says that the most important thing is to get a result before your competition. And when that's the environment that you're working in, you tend to make decisions based on fear. So I would argue that the reason that Bicep 2 made these decisions based on fear is that they were operating in such a toxically competitive environment that it became dysfunctional. So whether you think competition is really good for science, really bad, or somewhere in between, I think that this case study shows us that it's really worth thinking about the ways that we systemically and interpersonally encourage competition and how that might jeopardize our ways of knowing. But I want to leave you on a hopeful note, and that's that Planck and Bicep 2 are actually teaming up. The next generation of CMB instruments, they're going to combine their resources and their know-how to go after this really important discovery together. So the final thought that I want to leave you with is that competition might be the most efficient route to a result, but collaboration is likely the most efficient route to a reliable result. Questions? Okay, that's a great question. The question is, who the heck is funding this experiment such that they're allowed to go out and publish false results? Okay, so actually I believe that Bicep 2 is funded by an independent philanthropist named Jim Simons. I don't know if that has a direct correlation with, the decisions that they made. I would argue, some people say yes, some people say yes. And that could be true, but I would argue that it's also a systemic problem in that science is sort of built structurally to be a fear-soaked environment, and when you're operating in an environment like that, even if you're a great scientist, it's hard to make scientific decisions. Any other questions?
Why did Planck not share their data? What was the excuse they gave for not sharing their data?
Yeah, so I think Planck also wasn't free from operating, in a toxically competitive environment. I think Planck didn't share their data because they were being self-serving as well. And again, this isn't because any of these scientists are malicious people. It's because structurally, science is built to work this way. It's built to encourage competition. That's a great question. So the question is, how long does peer review usually take? Having not actually written a paper myself yet, I'm not sure. But from what I can tell, it can take anywhere from like a few months to 6 months, 8 months. Years? It can take quite a long time. Any other questions? Other questions? Okay, so Hector, another first-year grad student at UW, yay, just asked me another great question. He asked, if you think competition is a good thing, what would be sort of a safe way, a more moderate way to foster it? And I'm going to say the same wise words that were once said to me. I don't know. I don't really know what. Okay, so my colleague Beth Lee suggests that we encourage open communication throughout the entire process. And I would agree with that. But the point is that this is a really, really sticky problem that I think all scientists would agree that we're dealing with interpersonally and systemically in our careers. And I just wanted to throw it out there that maybe it doesn't have to be this way.